We finished this chapter by showing how the periodic table can be explained from quantum mechanics. The chemistry of an atom is determined only by its outermost or valence electrons. Those electrons do not feel the full Coulombic attraction from the protons in the nucleus because the inner shell electrons are repelling them. For a lithium atom, for example, the 2s electron in the valence shell sees a nucleus of charge +3 that is shielded by 2 electrons in the 1s orbital. If this shielding were complete, then the effective charge felt by the 2s electron would be equivalent to z = 1. Because the 2s electron spends some of its time near the nucleus, the effective charge is somewhat greater than 1. For lithium, Z effective is around 1.26. Using effective charge, one can estimate the ionization energy for the outermost electrons of much heavier atoms. As we move down the periodic table, Z effective will increase, but the outer shell electrons will have higher principal quantum number, making the ionization energy smaller for heavier atoms. The Pauli exclusion principle tells us that no two electrons can have the same set of quantum numbers, where 3 of our quantum numbers describe the orbital and 1 describes the spin. We often call these two spin states spin up and spin down. Thus, each orbital designated by a box, or simply a line, can have at most 2 electrons. When we have 2 electrons, one is spin up and one is spin down, and we call this spin pairing. In atoms with more than 1 electron, a given electron will be repelled by the other electrons. This can be described as a modification to the Coulombic potential energy as an additional term due to the electron repulsion of opposite sign from the attraction to the nucleus. Here, Z is the effective nuclear charge that includes the screening from the other electrons. This change in potential energy gives a difference between electrons in different orbitals. As a result, electronic states with the same principal quantum number but different angular momentum break their degeneracy and split into orbitals of different energy. This causes the S states to have slightly lower energy than the P states, while the D states are considerably higher in energy. Let's consider the electronic configurations for the first 5 elements, where each box represents a 2-electron orbital. Hydrogen has simply 1 electron in the 1s orbital. Helium has 2 electrons that both go into the 1s orbital in a spin-paired configuration. Lithium, with 3 electrons, has 1 electron that must now go into the n = 2 shell. In this multi-electron atom, the S states are lower in energy than the P states, and so the single electron goes into the 2s state. The 4th electron for beryllium joins this electron in a spin-paired 2s state. The 5th electron in boron begins to fill the 2p states. To add more electrons, we need to use some of Hund's rules. It turns out that 2 electrons spin-paired in the same orbital has higher energy than 2 electrons in different degenerate orbitals. It also turns out that unpaired electrons have lower energy if their spins are aligned, meaning they're pointing the same direction. Both of these results come from a slightly reduced Coulomb energy for these electrons. For the next atom, carbon, with 2p electrons, Hund's rule tells us to have both electrons in different p orbitals but with their spins aligned. Similarly, for nitrogen, the last electron goes into the remaining p orbital with its spin aligned with the other 2. Oxygen's next electron then begins spin pairing the p states. Fluorine then spin pairs another p orbital, and then for the noble gas neon, all of the states in both the n = 1 and n = 2 shell are filled with spin-paired electrons. From the energetic ordering of these quantum states, we can then explain the shape of the periodic table of elements. By filling states with lowest energy first, we start with the 1s and then the 2s electrons. On the periodic table, these are the first 4 elements in the s block. Then we move to the 6 electrons that can fit into the 2p states, which starts the first row of the p block. The 3s and 3p electrons are next, filling in 2 elements in the 3s block and 6 elements in the 3p block. The 3d orbital is similar or slightly higher in energy than the 4s, where we fill in the 4s elements first, then the 3d, before moving to the 4p. The rest of the periodic table, including the F elements, can be built up in a similar fashion.